Our next speaker, well known to all of us, Giorgio Gratta, and he is going to tell us about a different kind of long baseline reactor neutrino oscillation.
Okay, so I guess yesterday I mentioned that I came here essentially with the idea of competing with Stan. That's when Stan was starting the Minos, the neutrino program using accelerators. And so being contrarian, I was actually going to work on reactors. And I think it's as I was putting together the slides, I realized that in fact that was, we're very lucky more than once, or at least the community was very lucky more than once. So that's the case, we usually think that nature is misbehaving or trying to trick us and all this kind of things, but that's the case when nature was sort of kind. In fact, in my career, I've seen nature being kind 3 times, I guess, twice with reactor neutrinos, and once actually Barry will tell us about. I think it's fair to say nature was also kind for gravitational waves. So the principle here is to actually make a electron neutrino, or actually electron antineutrino, but from now on I'll just call it neutrino because to save time. Disappearance experiment using the fact that reactors are very intense sources of low energy neutrinos, and then placing a detector at various distances or at a certain distance, and actually studying the disappearance of those electron neutrinos on the way to the detector. The nuclear physics of this at first order is really simple, but then of course, if you want to do it right, is horrendously complicated. It turns out that actually doing it simple gets you almost there. So this is actually that's the reassuring part. And so if you just take, there's typically, most of the power of the reactor, and I'm talking about essentially commercial power plants here, burns for the most part 4 different isotopes, 2 isotopes of uranium and 2 of plutonium. And as an example, U-235, it eats up a neutron, it gets fissioned by a neutron, and it makes 2 fragments plus 2 neutrons, which then in turn continue the chain reaction. Then you can actually look at what's the probability of what's the distribution of fragments you can get in terms of mass number A, and you see that most of the cases you get around 94 and around 140. And the stable nuclei there are zirconium 94 and cerium 140. And so when you can add together the neutrons and protons of those guys and compare them with the ones of uranium, and you see that in order to reach stable matter, that is those 2 guys, you need on average to turn 6 neutrons into 6 protons. That's essentially the basics of this. And so when you do that, those are beta decays, and so they produce your electron antineutrinos. Unlike accelerators, those are very pure sources. There's nothing else. There's not enough energy to do anything, any other type of neutrino. So that's all there is. In addition, each fission, your friend nuclear engineer will tell you, makes 200 MeV. And so you can actually now, from the power of the reactor, which is typically 3 gigawatt thermal power for modern reactors, you can figure out how many antineutrinos you make, and that's about 6 × 10⁻20 antineutrinos. Okay, so that's very simple actually. This part is simple. So now you have to detect the neutrinos, and unlike high energy, the energy counterpart of this is sort of tricky because at those low energies, it's hard to. Sometimes you get fooled by other things. So they start being low background experiments, and they tend to go underground in various ways and so on, because you want to protect from cosmic rays, and you also need your materials to be reasonably selected for low intrinsic radioactivity. And I kept saying carefully, reasonably, and so on, because I'm working on double beta decay now, which it's way it's way more difficult actually. One reason why this is not particularly difficult is that you actually, what you do is that you use inverse beta decay to actually detect your neutrino, where your antineutrino now is important as an antineutrino interacts with the proton, you get a positron and a neutron. The neutron hangs around a little bit, needs to be thermalized first, and then eventually needs to capture. And when it captures, it emits, if it captures on hydrogen, 220 keV or 2.5 MeV, 2.2 MeV gamma ray. Some of those detectors actually mix in the material that is scintillator. They mix gadolinium, which produces a big shower, much more energetic, so it's easier to detect, and it has even lower background. But that's kind of a detail. So you make a gamma, but before that gamma, you get the two 511 keV photons from the positron annihilating in your whatever material that might be. So it's actually a nice signature, because you get you get the 2511, and then after a while you get the signal from the capture. In fact, the 2511 come together also with the energy from the positron that has to slow down, and so the prompt signal measures the energy of the neutrino, at least to some extent, and then the capture signal is just your tag, is the thing that tells you that that was the event you're looking for. Okay, so this has been around for a long time. People have known this for a long time, and again, from the kinematics, you can reconstruct the energy of your antineutrino. So there is actually an interesting plot to actually to keep in mind about this, and that is the fact that the reactor spectrum has a shape that looks like this. The higher you go in energy, and the less decay, then the less neutrinos sort of it makes. At least prompt neutrinos. Remember, there's all the spent fuel of your reactor that stays radioactive for very many years, and it keeps emitting neutrinos. But at that point, they are dilute in time. And they also become lower energy, so they go essentially below threshold. You don't see them anymore. But in terms of prompt flux, you get this kind of sort of shape of the spectrum. On the other hand, your cross section for detecting them with the inverse beta decay is this green curve, and so the spectrum you'll see in all the subsequent slides is this thing here, which is essentially the convolution of those two things. And that's what you see is the blue line, but the real spectrum is the thing that is shown there. The red curve is showing there. The inverse beta decay has a threshold 1.8 MeV, so that in practice, out of my 6 neutrinos per fission, you only get to see 1.5, and that's it with this kind of thing. Now, this issue of using reactors for as sources of neutrinos is, of course, a very old one, and it's got, let's say, a glorious but somewhat checkered past. Glorious because that's the way neutrinos were discovered. They were invented by Pauli, and then in the 50s they were discovered at Savannah River by Fred Reines and Clyde Cohen. With neutrinos coming from a reactor, and with a liquid scintillator detector that maybe Fred Reines, I don't know if this is Fred Reines, was working at this in this picture. But I say checker paths because the signal of those things are not particularly impressive. And the original physical review paper that essentially where all this was started and the neutrino discovery sort of originated, had an excess. This is reactor on minus reactor off. Had an excess which is like 2 sigma. So this is actually not a very impressive thing. And when this, so there's been a number of experiments of this kind in the past, and some, including oscillation experiments, some in Europe, some here in the US. And this was somewhat, was not a brilliant thing. There were all sorts of confusing results, and so on and so forth. But then things change, when nature was kind enough, that makes us, and of course we got better. But the combination of us being better and having more sophisticated experiments and nature being kind really changed how this worked out. And I'm claiming that the modern era starts with the Shaw and Paloverde experiments, Shaw in France and Paloverde here in the US. and which is also, those are the last two experiments where oscillations were not observed. So you get lucky, but up to a point. Okay, and actually, this is a picture, a typical installation with this kind of things. This is the Palo Verde experiment. The detector is sitting underground in some sort of artificially dug pit somewhere about 1 kilometer away from the reactors. As it turns out, Palo Verde has 3 reactors, roughly equidistant from the detector, and the detector is essentially a liquid scintillation detector. In this case, segmented, but that's sort of inessential. The show was very similar. There are 2 reactors and was in a place where food is better, but that's essentially very similar. In that case, the detector was homogeneous instead of being segmented. So at that time, when I say we're younger, we're really concerned that this was again that the field had some sort of not a particularly good reputation, and so there were all sorts of checks were done, including the fact that Shaw was lucky enough to finish building the experiment before the reactor started. They were working on a brand new reactor, whereas we were actually using an existing reactor. So they saw the power come up when they turned on the reactor, and they were measuring at the same time the number of antineutrinos they were seeing. So this is the power, this number of antineutrinos, and you see that there was an excellent correlation. So they were quite happy to report that this was no fluke or anything. They were really this was a real thing. So Andre told us everything about mixing, neutrino mixing this morning. For a while, I'm going to actually simplify things and use the fact that there is, as we've seen, a small energy gap, a small delta m squared, and much larger delta m squared. So you can sort of think in terms of two-flavor oscillation, at least initially, and that simplifies the notation quite a bit. So we are going to essentially do an experiment now where we measure probability that a neutrino changes into something else, but in particular, a neutrino disappears, and there's no other flavors sort of around this. And just for simplicity, the parameters in there, this is actually done with units that work out well when you plot them, if you want. So the energy of the neutrinos is MeV. The delta m squared is electron volt squared, so there's a mix of units, and the length is in meters. So how difficult the experiment is depends, as I said, how on how kind nature is. And let me explain. If I'm just about to see oscillation, that is, if the mixing angle is very small, then of course this makes things really hard because you're looking for a very, very small effect. But in addition, if you're not at the right distance, or let me just read it out. If you are at the right distance, and in particular L over E, that is distance divided by the energy, is just right, well, then you use your mixing the most, the best possible way. And we'll see later in some plots that it pays to be at the right distance. So if you're at the right distance, you see the most depletion of the flux, and so you are, you can actually do the best possible measurement. Furthermore, since the reactor, as I showed you before, emits a continuum spectrum, so there's actually many, many energies in this, there's a continuum of energies in here, you are exploring at a fixed distance different delta m squared, and you get like a hole just at the right place, at the delta m squared place. And so now you can use that energy to measure exactly what is delta m squared. All right, so that's actually the result where there's no result. There's no evidence, and this to the left is the show data. You can see the spectrum, which is, just binned, the same distribution I showed you before, and you see that there's no deficit, to speak of at all. So that's and then this is actually the final plot. This is again in this two-flavor approximation, sine square to theta versus delta m squared. Here, delta m squared versus sine squared to theta. This is the old atmospheric neutrino from Kamiokande that you've seen this morning from Jenny Stoke, I guess, or Andre Stoke, or both, I don't remember. And then you see here, and I mark this thing. So at large delta m squared, that is sort of up this way, though this is actually, those are the limits, if you want, that you set in the mixing parameter or in the sine squared to theta. For Palo Verde was 0.17, and for Shaw was better, was 0.1. I'm stressing this because you will see what it means to be lucky next, in the next few slides. All right, so that's those are the limits that were obtained at this point. So then, we didn't give up. We said, okay, so this was actually the region that was inspired by the atmospheric neutrinos. That is the delta M squared that was inspired by the atmospheric neutrinos. But there was another puzzle that was the solar neutrino puzzle, and there the delta M squared is smaller, which means if you remember the formula, you have to go way further away in distance. And so then this is not built at a power plant, but it's built at you use all the power plants that there are, as it turns out, in Japan. Japan turns out to be very convenient for this. First of all, in those days, they had lots of good fraction of their electricity was produced nuclear, so they had lots of nuclear reactors. After Fukushima and stuff, they turned off quite a few of them. In addition, there is actually another somewhat unappreciated kind of feature. Japan is a small island with no rivers, essentially, at first order. That means that if you want to cool your reactors, you need to put them on the beach because there's no rivers. And so if you go under the mountains in the middle of the island, you are more or less equidistant from like some sort of a corral of reactors. And so that's what's being exploited here. This is, of course, a rough statement. It's not exact, but Kamioka, the mountain and the lab was in a favorable place, surrounded by all these reactors. And of course, at that point, you have to start going really deep into the ground to actually to have better shielding, because the detectors start being quite large, and it's a kiloton of liquid scintillator. In this case, in the previous case, we had gadolinium. In this case, you give up the gadolinium because it gets too complicated. And so, okay, that's the detector. Use the famous Hamamatsu very large photomultipliers, and bam, now you see that's sort of unmistakable. The spectrum has a big hole in the middle of it. Okay, so that's what it means being lucky or having nature cooperating. So we're not quite at the right distance, but almost exactly at the right distance to produce the maximum effect. And the effect essentially chooses the right, or the energy where the effect is maximum is more or less in the middle of your spectrum. Okay, so there's no doubt, no matter whether you believed before in the reactor experiment, and so on, there's no doubt that this is a signal for oscillation. There's pretty much nothing else that can do this. And in fact, we have, there is actually, this is a nice plot where you're actually showing L over E, that is the parameter that goes into the oscillatory term. And there is actually a funny scale here that is linear for Kamland, and then it becomes logarithmic here, so you can plot all the older experiments at shorter distances. And so you can see at shorter distances, everything is right on one. I'll tell you a little bit more about this later. For the time being, it's good enough to say it's right on one. And then there is this clear sort of oscillation thing. The way I scan the distance here, does L over E is to change, to interpret each E, in the appropriate way. And the reason why what you see is not the dashed line that is a nice sine wave, is that there's no fixed distance. I'm using the most probable distance here, but in fact, there is a family of distances. So there's some sort of blurring effect due to that. And I'm just saying that, Super Kamiokande had for different kind of with atmospheric neutrinos, had the guts of writing a paper titled on the oscillatory behavior of neutrino oscillations. And PRL let them do that, and we never dare doing that, which is kind of unfortunate because this is clearly the oscillatory behavior of neutrino oscillations. And so a different way of seeing the same thing is actually this plot here. And see, again, these are the old experiments. This is now all log scale. And you can see where Kamland is. So it's not quite at the right distance. The right distance would have been this one. But nevertheless, it was actually good enough to do the experiment, and this will come in a moment, the right distance thing. Again, just to emphasize how this thing works, since you're selecting the energy tells you exactly where the oscillation is happening in a sense, you're measuring delta M squared really well. This is a maybe slightly old plot, but it makes the point. So you see that our oscillation region, that is this bluish kind of thing, is very narrow in delta M squared. You're measuring delta M squared very well. You're not measuring 10 minutes left. Okay, thanks. You're not measuring particularly well the mixing parameter, because measuring rates, absolute rates, is hard. That's actually when you have to be sure that the flux of the reactor is what you expect and all that. So now the next thing is that, well, okay, how do we get? Is there a way of getting to θ13? Because we've measured, we're not successful in measure the atmospheric neutrinos. We're successful with the solar neutrinos. Now the idea is whether you can actually get go back and measure θ13. And remember, we got down to 10% mixing with Shaw and Palo Verde, with Shaw, and then 17% with Palo Verde. So now you need to be able to do much better than that. And at this point, that's actually beyond, this is not my work. But there was some people thought that this is actually that this can be done with reactors. And actually, first person to actually point this out was Mikhailian, the Kurchatov Institute in Russia. But this thing was then taken on by Yifang, who actually started with Palo Verde and then Kamlan here, and then also experiments with double Shaw and Reno in Korea. So there are actually 3 of those experiments. And the idea here is that this is hell. This is going to be really hard because you have to go down to probably 1%. God knows how small the mixing angle is. And so they devised all sorts of really clever ways to actually calibrate the flux. And in particular, and I'm talking mostly now about Diabate, that I think was actually first to actually devise all these things. They had many detectors which are all the same. And so their fiducial mass, if you want, was segmented or fragmented in, I don't know, 6, 7, 8 detectors. And then in their view, they would actually take data in some near site and a far site, and then reshuffle them as they would go, so that you cancel all sorts of systematics and so on. So that was actually, they really wanted to do this right. And they put lots of energy or emphasis into this. All right, so we can skip this. In this case, okay, now we're back to about a kilometer sort of baseline, except there are 2 baselines because they have a near site that is here, that is essentially the control sample in a sense, and this is the far side. Notice that once you have this segmented detector, this detector made out of different lumps, you can choose where you put more your statistic or more your mass. And so you can essentially put, in this case, 4 detectors at the far side where you have lower flux, and then 2 detectors near the reactors to calibrate the reactors. But you can essentially reshuffle those things. Okay, so that's actually what the idea is. And then when you turn it on, you know what? This mixing parameter is 0.09. So we're so close. Actually, Shaw was really, really close to this. They could have discovered this 10 years, 15 years earlier, essentially. So again, this second time we're really lucky. Or at least, so they built this really fancy thing, which is great because then it was really, a clear signal. But, could have been done maybe with less of an effort. And so you can see here also, again, in this, with this weighted baseline thing, I don't even know exactly what, but essentially this is kilometers. This is the near side, this is the far side. And again, you can see that the flux is right here and it's not right here. And again, you're measuring the delta M squared. Then the next generation, which doesn't exist yet, but Andre, I think, sort of mentioned this morning, is even more ambitious. And so the idea now is that, okay, so you actually go, remember I told you that Kamlan was not exactly the right place. You go exactly the right place. You have a near side and a far side. And then in particular, you actually look at this sort of oscillation here, because that thing encodes something interesting. So the frequency of this, θ12, that is the old Kamlan parameter, is how much the flux is depleted. And again, this is the most depleted possible. So you get a really large effect here. Remember, the mixing parameters in neutrinos are large in general. And then you get this subdominant or high frequency modulation here, which is really, whose frequency or period measures delta M 2.3 or 3.2. And in fact, the phase of this oscillation is supposed to discriminate between normal and inverted hierarchy. And so the idea is to actually go after that effect. Now, this is now really challenging. And so the first thing, let me just say, we're not used to this in particle physics, but the idea is that, of course, the effect is very small, but you do essentially Fourier analysis of this thing, which is the thing we're not used to. And so you use all of the periods, the phase at various places to actually tell whether it's the blue line, the blue line or the red line is what you're measuring. You need a humongous size detector in order to be able to actually, to have enough statistics to map this kind of rapid oscillation. The details of the reactor don't really matter. So again, all that stuff about complexity of reactors, it doesn't really, that's not the important thing. But then you need very good energy resolution because otherwise this thing washes away. So that's the way the detector looks like. And just for fun, I overlaid, roughly speaking, the size of Cumberland and of Shaw. So you can see how large this thing is. This is essentially the largest scintillation detector ever built. It's 20 times the size of Cumberland and 40 times the size of Wojcicki, to give an idea. And the resolution is supposedly, hopefully, is better than either one of them. In fact, it's twice the resolution of Wojcicki and 5 times the energy resolution of Cumberland. They do this by clustering everything with photomultipliers and collecting really as much light as possible. And also they developed some fancier photomultipliers that have essentially higher, not so much quantum efficiency, but efficiency for detecting light. And they are, busy building this thing with the idea of being finished in 2024. So in the last 2 minutes, not everything is, is good. If I now remember, I told you at the beginning, you can see a short baseline, everything matches out and everything works out. That's not quite true. If you blow up that plot, this is now the flux, the flux 1, that's the flux you predict or calculate. And these are all the data points. And this is kind of mostly old experiments, but modern experiments now, for other reasons, essentially need to have the near detector with very, very small error bars. And when you put it all together, there is a deficit. And so this goes under the name of reactor anomaly. I think most of us, I would say, believe, I'm not an expert anymore, but most of us believe that this is probably that we don't calculate the flux of the reactor well enough. Those calculations are really complicated. So the number of beta decays that go in that kind of calculation is about 10,000. So there's 10,000 different branches of beta decays you have to account for. So remember I said at the beginning, the basics are really simple, but to do it really right is really hard. And so that's actually what the thing is. But some people, maybe Andre hopes that this is actually something to do with sterile neutrinos, and this is really work in progress. And so that's actually my summary. Reactors can, are not only good for making electricity, they can also make neutrinos, which are more fun. This is actually something which in recent times has really matured from some sort of somewhat shaky grounds, has matured to be a very respectable and in fact effective technique. And here again, I'm showing you at different baselines, what kind of things, which kind of experiments there are, and what kind of physics is addressed. Thank you.
All right, thank you, Giorgio. Questions? Yes, Jenny.
Can I actually take exception to your penultimate slide there, where you're still talking about the reactor anti-neutrino anomaly? I take exception to that because that paper that you're referencing there has debunked it.
Well, I think this is still something. There's still people that are.
The point is, the problem is that it is continually talked about, and that's why studying it, but it's gone.
Okay, yeah.
Thank you for saying
there's-
that. I was hoping someone would put that out.
I also said that I don't believe
Uh-huh.
there's also all sorts of bumps. There's also some high energy kind of dip or bump or whatever, which is again likely to be just that we are not particularly good at
Talking about
that.
5 MeV.
Yeah, there's the 5 MeV. I don't know what they call it. No, it's not a bump, it's a dip. So I don't know.
It's a bump.
It's a bump. Is it a bump?
It was in the Palo Verde data that you showed.
Yeah. Okay. So yeah. No, I remember. Yeah. So, yes. But okay. So I forgot.
called a
So it's
hump.
backwards. It's
It's
like
a hump, not a bump.
it's a hump. Okay.
Right. Okay, yes, go ahead.
Giorgio, just a very naive question. With reference to CamLand, there's this uncertainty on L over E because you don't really know which reactor your particular interaction comes from. So I would, is that smearing the mixing angle more than delta M squared? I would have thought it would.
No, that is smearing mostly that squared.
Because it's multiplying delta M squared.
Right.
Okay.
That is smearing mostly that term squared. You know, the regrettable thing is that really nice signature of the inverse beta decay with the delayed neutron capture and all that also erases all sorts of directional information that you might have. If you are using electron scattering, neutrino electron scattering, your event would, like in the solar neutrinos, would actually point back at the reactor, and so you would be able to measure, to essentially assign a distance to each event. But with the inverse beta decay, you cannot do that.
In all the years of running, for example, for CamLand, were there periods of time when some of the reactors were off?
Yeah.
So, and could you not piece together the different data sets to
Yeah.
deduce or
Final
unfold?
fit, actually, Bruce probably knows more than I do on this. I think, yeah. So look, the full analysis takes care of all this, and but I showed you the conceptually simpler thing that so you get it. But yes, I mean you can do some of this. Unfortunately, there's you cannot reactors produce lots of electricity, and that's very valuable. So it's very hard to control them. You can't just say, okay, you guys in that direction turn off for 2 months, and then you guys do it, and that's not possible. So essentially, you get random reactors turning off for refueling, and each of them contributes a small fraction of your flux. So it really doesn't mean much until you get the earthquake, and then they shut all down, and that doesn't help either. Well, I mean, actually, it helps because you measure the background and all that. But then when they do it, when they are off for like 10, 15 years, at this point, it'd be nice to turn them on again. But now they're doing other physics, so that's it's a finished experiment.
No, we're still doing that as long as we're running. They're always coming in. So
It's always coming in. Yes.
So reactors are. The projection is that more of them will be coming on starting soon. And one of the ones that I believe is coming on is actually on the peninsula north of Toyama. That has that's much closer. In fact, before the earthquake, we were expecting that we'd have a later section of the data where there was a much larger contribution from one near reactor. And so that average L0 would actually be different in later data than earlier data.
Yeah.
What we got instead is the data constraint with all the reactors off, so, which is also very useful.
Yes, go ahead.
Just really quickly, your statement about how Super K dared to state that they had neutrino oscillations and CamLand did not in the title of the paper.
I was just making a joke about the language used in the title of the paper.
Yeah. So my question is, were those contemporary papers ish?
I actually honestly don't remember, Robin. All I know is that we were considering a title, kind of a funny title like that, and then it's oh, come on, the editor is gonna reject it anyway. And so we did it. And then somebody said, oh, okay, had a paper exactly with the title.
So
yes, but I don't remember. I mean, look, it's not very important.
Okay.
I think this is I bet this is the paper when they really had very, the final evidence of the atmospheric neutrino oscillation, which was a very impressive paper. But I'm not taking any. It's just kind of a funny title. That's
Okay.
all. I mean,
I actually remember it very much as a race within Super K, that we were working to identify a high resolution L over E sample.
Yeah,
Because we knew that CamLand was coming out with that
Ah.
plot. And we were working very hard to get the results out.
but is that the paper that we title
Yeah,
on the
yeah.
oscillator?
It's the
Okay,
one,
all
it's the
right.
one where we see the dip
Yeah,
and it
that-
comes back.
Yeah,
I
but
mean-
that don't make sense, because you normally don't see an oscillation, you see a piece
Yes.
of the sine wave.
Yeah.
So the first people who saw the up and down motion, there's something to that. Yeah, and the Camlin one is the prettiest one, man.
Camlin is the prettiest one, and but we were, a few months after snow.
Yeah.
By the way, in the neutrino oscillation race, we missed that by a few months.
So there's one other thing that I want to comment on, which is your initial argument that in inverse beta decay you have a threshold. However, if you were to employ coherent scattering, you actually access a tremendous number of neutrinos,
Yes.
but it's obviously there are other difficulties. In fact, there was an idea to do this at one of the research reactors.
Mhm.
We actually published a paper on that. Where not only that we could potentially use coherent neutrinos, but coherent interactions, but also move the reactor, not the detector.
We have a paper with Ifan Wang, which is probably 25 years ago or something, where we proposed having the large detector stationary and then using a nuclear propelled vessel to actually
Yes,
and so
the reactor I'm talking about actually exists.
okay. Well, I mean, nuclear propelled vessels do exist. No, but in fact, actually, we had a very specific thing because it is not entirely reasonable to say that you use a submarine, and this is they have nuclear icebreakers. The Russians have nuclear icebreakers, so we had numbers specifically for the case of one of the icebreakers, which are completely non-classified, at least used to be. Who knows now? Maybe they reclassified them, but.
Okay, any other questions or comments?
I just wanted to say that about what you were just saying, there is an experiment for current neutron nuclear scattering in Texas, where you have the reactor that is moving, and the experiment is called MINOR.
Minor, yes.
Yes.
That's
So
what I
it
was
is,
referring to.
but it is, it is happening. It's not like, not.
Not really.
Okay, so a year ago, it was still kind of there, so that's why,
Okay.
But the idea is what I want to point it out.
All right, well, thank you. I think we're going to close this session, go for another coffee break. Giorgio, do you have any instructions for us?
No, I don't think so. There's coffee outside.
Okay. So